Everything in mathematics has a forward and a backward or an undoing. And so we need to be able to undo exponents. And we're going to do that through a radical. So let's just go ahead and look at exponents here again for a moment. 3 squared is 3 times 3, which is 9. And so if I want to see a picture, what it's telling me is I have a square that is 3 by 3, and I have 9 total squares in that larger square. So the area is 9. In this square, it's 4 squared, so that means I have 4 times 4, dimensions 4 by 4 on this square. And if I was to count up the area of this 4 by 4, I would get 16. And likewise, 5 by 5 has an area of 25. So I would just make a square that has sides 5 by 5. So what we do with the radical is we undo this exponent. And a radical, it's a little bit like a division sign. It kind of has this little hook out here, and it's an undoing. So when I say I have a square root of 9, it's asking me to go backwards. So if I have 9 in my square and I want to go backwards, it's asking me what were the lengths of both of the sides. Well, if it's a square, those lengths are the same, and the square root of 9 then is 3. And going backwards, it would just be saying take this square that was 4 by 4 that made 16, and now that you have the 16, go backwards and tell me the length of each side that provided me with 16 as an area. And the square root of 25 is 5. So when you break this down, you have 5 squared. This square root symbol really reduces that power of 2. This square root symbol takes off that squared on the 4 squared, which was 16. So when I say I have the square root of 1, it just means I have a square that's 1 by 1, which has an area of 1. How long are the sides? They're each length 1. The square root of 100 is 10. So if I had 100 inside, what would be the dimension of each side? And the square root of 36 would be 6. Again, I can look at that as 6 squared. These actually reduce and leave me with a 6. Same with the square root of 100, which is 10 squared. So we like to know these square numbers. We also like to know cube numbers. Now, cube takes me into 3 dimensions instead of 2. So when I have a cube, such I have drawn here, and I need 8 total. So what I need to see here are 8 squares within this cube. And if you count up all those little boxes, you should end up with 8. And so there are 8. So what it wants to know are what are the lengths of each of these dimensions, and they are 2. In other words, if I had 2 by 2 by 2, that would give me a total of 8. Cubed root of 27 is asking the same thing. It's just a little bit bigger. And if I go ahead and divide this out into smaller cubes, you're going to see that there's going to be dimensions of 3. The height is 3, the width is 3, and the depth is 3, because 3 times 3 times 3 is 27. So again, that cube root and the exponent of 3 end up reducing. The cubed root and the exponent on the 2, which was also a cube, to make the 8 reduce. So looking at variables, knowing that these two are going to reduce, they look at as a fraction, my answer is x. So again, the 7 and 7 reduce to a 1. Now I have 6 and 3, and that's going to reduce to, we'll go ahead and write this out, that's going to reduce to a 2.